morning, Explorer. Or is it evening? Who knows under this ocean blanket? Now, let's wipe that taxed look off your face. Oh, well, that is your face. Oops. Get ready to tackle our next big task. We can't ignore this any longer. Our battery levels are going critical. Our hero experiments and shipboard lighting barely draw anything. But what's killing us is just keeping things warm. I've had to shut down sections C to F, so no more jelly parkour, I'm afraid. Our solar array, which normally bathes in glorious sunlight to charge our batteries, is as inactive as a frozen comet. It's imperative that we restore it. Luckily, our kit is equipped with materials that have been waiting oh so patiently to be introduced. Photoresistors. For our training purposes, it's enough to know that photoresistors also react to light like solar panels, but in a different way. Photoresistors react to light like summer flowers. When the sun rises, flowers open. When the sun goes down, flowers close. With photoresistors, when they receive light, their resistance decreases, allowing more current to pass, or higher signal levels as read. In darkness, resistance increases, choking current, lowering signal levels. We can use this to simulate our solar panels receiving sunlight. So, brace yourself, dear Explorer. Day 6 begins and we have a solar system to fix. Let's get to know our newest shining star, shall we? This little device is also known as a light-dependent resistor, or LDR for short. The resistance of a photoresistor decreases with increasing incident light intensity. In simpler terms, when there's more light, the flow of electrons becomes easier. When there's less light, the flow becomes harder. Think of it as an electrical component throwing a more light, more fun party. Photoresistors are made of high-resistant semiconductor material. Whew! Try saying that 5 times fast. When light hits the device, it absorbs the light photons. This absorption process provides energy to the electrons, which makes them jump from their valence band of orbits to the conduction band. This leap means the electrons are free to move, thus reducing the material's resistance. It's like magic, only its scientific nature is backed up by empirical evidence and testable explanations. Essentially, a photoresistor is a sensor that allows us to detect light in the way that a solar panel uses it to generate power. They are the key component we need to simulate and fix our solar array today. Remember, they are small and sensitive. Treat them well, and they'll return the favor in kind, Explorer. Moving right along, let's delve into the slightly more complex topic, the concept of analog and digital signals. Do bear with me, Explorer, as this will be vital for us to understand our photoresistor readings. All right, analog signals. These are continuous signals. Imagine a dimmer switch connected to a light bulb. The dimmer can be adjusted to any level between on and off, providing an infinite number of positions of brightness. This is like an analog signal where the values can fall anywhere within a certain range. In terms of microcontrollers, they are a bit more complex to handle due to their nature of being prone to degradation and noise interference. What this complexity does, however, is allow them to represent numerous amounts of information with the potential to provide more accurate and refined data. Unlike analog signals, digital signals are discrete and can only be in one of 2 states, which are usually represented by either zeros or ones, meaning low and high. Picture a staircase. Each step you take is a definite value. There are no in-betweens. While they might not be as smooth or precise as their analog counterparts, digital signals are highly resistant to noise and easy to work with in terms of programming. Most of our microcontroller functions, like digital write and digital read, work with digital signals. So, where do our photoresistors fit in? I'm glad you asked. The value they provide, based on light intensity, is an analog signal. It can theoretically be an infinite number of values. That's why, to read these values, we need to use a different set of functions that can handle this variety, the analog functions. But more on that when we dive into the code. In summary, remember, analog is like a dimmer, continuous and smooth, while digital is like stairs, definite and distinct. Got it? Great. All right, Explorer. I know you've been wondering why, of all the many pins, we specifically chose the A0 pin on the hero board for our photoresistor. Well, let me break it down for you. You see, A0 is an analog pin. Now, our photoresistor isn't just a simple light or no light type of device. No, it's much more refined than that. It measures how much light there is. It's like the difference between asking if there's food at a party and asking how much food is there. I mean, a few crumbs of chips don't really count, do they? Anyway, because we want a wide range of values and not just a 0 or 1, we need an analog pin, hence A0. It's really as simple as that. Analog pins for analog devices, digital pins for digital devices. Well done, Explorer. You've digested all that analog and digital chit-chat pretty well. Now, let's shift our attention to the programming part of our task. And what do you know? We've got another new tool in our kit to introduce, the Arduino Serial Monitor. The serial monitor is one of the most useful tools we have at our disposal when programming with the Arduino IDE. Think of it as a window through which your computer can have a conversation with the microcontroller. In this case, our hero board. With the serial monitor, we can send data to the hero board and receive data from it. It can also be used to examine the state of variables, to debug, which is the act of finding and removing bugs in our code, or, like we'll be doing today, to monitor the readings from our photoresistors. To access it, we'll need to start by including some code in our sketch to establish a serial communication. Then, when we want to take a peek at the data being sent from the hero board to the computer, we simply click on the serial monitor option in the Tools menu in the Arduino IDE. Ready to give it a shot, Explorer? Let's dive into the code and start using the serial monitor to get a sense of what our photoresistor is telling us about our power situation. We're going to start using some new commands today, starting with analog read. This function allows our hero board to read analog input signals, which is just what we need for our photoresistors. Analog read measures the voltage between 0, which represents 0V, and 1023, which represents 5V, and returns a corresponding value. In essence, when we use analog read, we're asking the hero board to take a voltage reading from a specific analog pin and translate it into a number we can use in our code. Reading and writing are two fundamental operations in hero programming, or any programming for that matter. When we read, we're taking data or information in. When we write, we're sending data or information out. In Arduino terms, reading is often associated with sensors or inputs, like our determined photoresistors. They read or gather information from the physical world, which is used to make decisions in our code. On the other hand, writing is generally associated with actuators or outputs, like LEDs or motors. We write to them to control their behavior based on the logic in our code. All right, Explorer, are you ready to put this into practice? Let's start with analog read and see what we can learn from our photoresistors. It's about that time. Let's turn to some instructional material that I was able to gather cached on the computer. I've also added this to your mission resources for future reference. Hurry on now.
Hello and welcome back, Explorer. This is now day 6, and we have procrastinated long enough on fixing your battery. We've done a good job of wasting your battery the last 5 days, but now we're finally going to actually do something about it and fix the battery. Now, to do this, we're going to be simulating solar panel charging using a photoresistor. This is going to be a new input device that I'm sure Astrid just explained a few minutes ago. So to do this, we're going to obviously have to wire this guy up. I'm going to start with our breadboard. Today's circuit's going to be pretty simple. We're going to have obviously the photoresistor, which is, let's go here. And we can wire that up right there on the breadboard. This is going to be, you can pretend it to be our solar panel for simulation purposes. Now, it doesn't actually act like a solar panel in the sense that it's not going to necessarily charge your board. But when you do deploy your solar panels up into the surface of the water and you do actually start getting charged, you can simulate everything perfectly using this photoresistor here. So to start, you know me, I always like to take the 5 volt, run it directly into the plus line here, and I like to take ground and I like to run it into the little minus line here. And I'm going to change the colors just so they're nice and pretty to look at. Now that we have the 5 volt and the ground lines hooked up correctly on these long lines right here, I can start to wire up the rest of our circuit. The resistor, photoresistor anyway, is going to need 2 things. One, since it's an input device, we need to specify a pin that we're going to be reading that device off of. So where we're going to be reading the value. And remember, the way that a photoresistor works is the brighter it is, the more it's going to let through, and the darker it is, the less it's going to light through in terms of voltage. So it needs two things. One line, which is going to be the voltage, and then the other line, which is going to be essentially what's coming out of it, which we can then read off of. So this very first one is going to be the 5-volt line, and I'm just going to put that right here on the right side. It doesn't really matter which one you end up putting, so if you do flip it on accident, it doesn't really matter. Next, we're going to take this is going to be the output line, and we're going to be using analog input 0. Now, the reason we're using A0 instead of, maybe why didn't we use pin 4 or why didn't we use pin 7 is because remember that this isn't just saying, is there light on the photoresistor? Is there or is there not? It's not a digital signal with two outputs. It's how much light are we reading off of it. It's a value of 0 to 1023. It's not something that's a yes, no, high, low, 1 or 0. So the reason we're using analog is again because the amount is important, and depending on how much we have is how fast we're going to be blinking the LED or how slow we're going to be blinking the LED. So I'm going to take A0 and I'm going to run it up into right here. Boop. And I'm going to change the wire color to, I'm just going to change it to blue. Now remember, we need to complete our circuit. If we don't have a complete circuit, it's not going to work. We're going to have floating values, and that's not going to be very good. So we fix this by adding one quick resistor. Now we can do this by adding one quick 220 ohm resistor and setting it into the ground. Again, we need to make sure the circuit's completed. If we don't have ground in here somewhere, we don't have a value to reference where 0 is, and so the circuit will just get really confused. So with that, the circuit diagram should now be complete and the photoresistor should be working. When I go to eventually hit simulate, there'll be a slider here basically to simulate how much light is going on the photoresistor. You can think of this as when we have our solar panels, how much light the solar panel is receiving, and we can blink our onboard LED faster or slower depending on how much it's reading. Hopping into the code. Right now it's in blocks. I don't want it to be blocks, so I'm going to go straight to text. As it always does, it starts with the default blink, onboard blink, and I don't want a single bit of this. So I'm going to be removing everything here and starting from scratch. Now, before we begin, we should always start by saying what pins we're using and just define them at the top, because as we reference them later in the code, it's going to make things a lot easier. We're obviously using A0 as our analog input, so we can just type in #define, and we can say photo resistor underscore pin, and we're going to say this is going to be A0. So anytime we say photoresistor pin in the code, we're going to be it's just going to automatically replace it with A0. This is just defining what pin we're using here. So let's go. Analog input pin. Next, we're going to go into setup and we're going to say what we're actually doing here. So we are going to be using the photoresistor pin as an input. So we can go here and we can say pin mode, photo. I'm actually just going to copy this because it's going to make my life easier. Photoresistor pin. And this is going to be an input. We're going to be reading what value it is into the board so that we can actually use that. So after that, we do have one more we need to set, and that's going to be, in this case, depending on how much light value we're reading, we want to blink the onboard LED faster or slower, depending on what it's getting. So we're actually going to have one more pin mode. And I'm going to say pin mode. Wow. As you remember from the lesson 2 and 1, LED underscore built in. And we're going to set this as an output. Wow, I cannot type. And with that, we should have everything we need for setup. Except, I'm going to be teaching a new concept today. I'm going to be introducing a little bit of debugging, a good tool for debugging known as the serial monitor. So if I go to serial.begin, this is going to start a new serial monitor sequence. So basically, what this is going to do is if I set it to baud rate of 9600, this is going to make it so throughout the code, I can make things that are known as print statements to help me know what's going on in the code as it's executing. So I can make it so as we're going through, I can consistently print out the value that it's reading on the photoresistor to the terminal. So we can actually see it right here in our serial monitor. So if we click up here, this is going to print a bunch of random statements eventually, once I make those statements, right down here in our simulator. And that's going to be really, really useful for knowing how our code is working live while it's actually executing. And that is going to be super useful here in a moment. Next, let's go down to loop. Now, every time we go through loop, our goal is to, again, read the value, and then, depending on that value, blink an LED faster or slower. But to do that, we first need to actually read what the value is. So, let's actually grab the value. I'm going to make this an unsigned integer light value equals, there's going to be a lot, so I'll go over this in just a minute, analog read. And I'm going to take this photoresistor pin and just copy paste because I'm lazy. Now, there's a lot going on right here, so let me quickly explain what all this is. This is a data type. This is the unsigned integer data type. An integer can go anywhere from negative whatever to positive whatever, depending on, I guess, what coding language you're using and etc. Generally, it might be something like negative, some very large number, some 24,000 to positive 23,000 something, right? Unsigned integer means that that first bit in the value of it is not determining what if it's positive or negative. It's simply just unsigned, which means the only values it can be in this case is going to be 0 or a very, very large number. And the reason I'm doing unsigned is because I don't really want it to go negative. I don't want it to go anywhere less than 0 because I'm going to say that pure darkness is going to be 0, right? So the unsigned just keeps it from going into the negative space for whatever reason. There really shouldn't be a reason for it to, but I'm just keeping it unsigned so it does not. Finally, I'm setting that value to be called light value. So anywhere I call and I want to say, hey, what's light value? It's going to give me whatever it read off of here, the resistor pin. As you remember in previous lessons, we have digital read and digital write. Digital read is used for digital inputs. Digital write is used for digital outputs. Analog read, as you might be able to guess, is used for analog inputs. So analog write, on the other hand, I'm sure you could guess we're not using that today, but that would be used for analog outputs. So with all that said and done, that is what this line is doing. It is simply reading what the value is off of the photoresistor and putting that into this variable here, saving it as light value. Next, we're actually going to start using the serial monitor. We're finally going to understand how this works and start using that here. So let's actually write a little debug statement, serial.print. And here I'm going to say just plain text, light value, a little space. And then I'm going to do another print statement afterwards, serial.print light underscore value. I'm going to print what we got from here in here. And I'm just adding this here so that we can actually read it a little bit easier once we get to the serial monitor. Now, actually, with that in mind, let's start a simulation. Let's get this going, actually. I think this isn't supposed to be there. Okay, so now that I've hit run, I can already take a quick look at what the serial monitor is outputting. Now, it's going very, very, very quickly. So you might not be able to read this, but right now it's saying light value 1023, light value 1023, light value 1023. And if you look at this resistor I have here, the light value is not changing because since we're in a simulator, I can drag it like so. And if I do, nothing changes. Okay, ladies and gentlemen, I'm back. I noticed I accidentally put the ground thing here, and so I switched it so that it was along this line lined up with my resistor. Now that I have that fixed, it is working as it should. At least you notice a little cut in the video. But as you can see, debugging happens to all of us. So even live on camera. Here we go. And we have now it printing the light value. As we take the slider here, we start at 366. And we can slowly increase it, slowly increase it, slowly increase. And it goes all the way up to, 366 all the way up to here where it's 1018. Now remember, we wanted it to be between 0 and 1024. So because of that, these values are kind of strange. And we can change the resistance of we can change our resistor value too, and we can actually do it live. And we can change it to like 54 all the way up to 974. Honestly, it doesn't really matter at the end which resistor you used because the values you're going to get are going to be different. And so that's a little bit of a problem, but luckily there's also a fix to that problem. So to solve this little problem, I'm going to basically need a couple of values that I want to set is going to be essentially the minimum and the maximum that we're going to be allowed to see. So if anything, I'm going to make just a sort of a dummy variable, but it's essentially just going to say this is the maximum and this is the minimum because we're going to need that in order to easily do any logic for our next step. So let's set a static unsigned int darkest light. And this is essentially going to be our minimum. And we're going to set this to light value. And I'm going to say static unsigned int brightest. This is going to be our brightest light is going to be also equal to light value. Now you might be confused what this is actually doing. We've already discussed what unsigned int is. We're basically just don't want it to go below 0, right? So we're setting it unsigned because there's no reason for it to go into the negatives. Static, on the other hand, allows it to save its value between runs. So every single time that we see a static variable, that means that when we go through the loop next time, it's actually going to remember what it was previously. So it's not going to essentially change it unless, of course, you tell it to. So static is going to so if we change something later on, it's going to remember it next time it executes the loop, right? We could put this as a global variable and then change it later on, but this is just another way of doing this. Finally, we need to have a little bit of logic in order to make this work. So obviously, if our darkest light or our light value is less than what our darkest light has ever been set to, then we need to set the darkest light to be equal to that new value. Same with the light value for the maximum. If we do go past that maximum at any point, then we need to eventually set the brightest light to be the light value for the minimum. And so we can essentially use this to calibrate, give it a really bright something really bright and then something really dark, just to kind of calibrate the maximum light when we actually open the simulation. So I can actually write that logic. If light, oh my gosh, you know what I'm going to do? Copy and paste. If light value is less than, essentially what it reads is less than whatever the darkest, the minimum has been at any point, then we're going to set the new minimum to be what it just read. Darkest light is going to be set to equal light value. Also, if the light value is greater than the brightest light, then we need to set the brightest light to be equal to that light value, essentially setting the new brightest light. And with that, now we have a way to calibrate the maximum and the minimum when we actually go into the simulation once it starts running. And then finally, we need a way to map this. Luckily, the Arduino IDE and the Arduino library has a function built in that allows us to do exactly that. We can actually map these values essentially to a maximum and a minimum so that everything can look really pretty and nice on our serial monitor. And also we can actually get the last piece of functionality working, which is to blink the onboard LED as we want it to be, either faster or slower. So we're actually going to calculate what our delay value is with the map function. We're going to use the minimums and the maximums values that we can read. We're going to map them to what they actually are, and then we're going to calculate our delay function using that logic. So let's actually do that. Unsigned int delay value, which will be used in a moment, is equal to map. We're going to set the current light value is what it is just read. Darkest light is going to be the minimum. Then we need, after the minimum, the maximum. The brightest light. So this is going to be the brightest light value. And then we need to know how fast and slow we want to be able to make this go. So this is going to essentially map. So if it's, for example, if the darkest light is only 34, but we want 34 to map to what the lowest is on the delays. So we can actually set those to be, honestly, whatever we want them to be. I'm actually going to go up and I'm going to create a global variable up here. I'm going to go way up to the top here. And I'm going to define, so we can change it later, so it's nice, good, clean coding. Define min delay in milliseconds is going to be 50. So the minimum amount of delay that we can have when it's, I don't know, for example, very, very, very bright or very, very, very dark, either way, is going to be 50, 1/20th of a second. That's going to be very, very quick. And I can also say define the maximum delay. So when it's really bright, if we want it to go really fast, we can set it to be 50. And then if it's really dark, for example, we can set it to be 500, maybe half of a second. And by having them up here, it allows us to easily change it if we ever want to change it in the future. So let's then map those values, this range of values, to our new variables we just created. And that would be max light and min light. Finally, let's use the serial monitor again. I love my debugging stuff as much as I can use it. So let's go serial.print delay value and serial.println, creating a new line, delay underscore value, whatever we just calculated using the map function. And I'm going to quickly, just to make sure the output looks clean in a moment, delete that super quick so it'll look cleaner in just a moment. So let's actually start that simulation, and then we'll get the last piece of code working in just a moment. Not max light, it should say max delay. So we can pop up the serial monitor here and we can actually read what's happening. So if I set it to the minimum value, which is 54, then the delay you'll see is 499. That's what it's currently mapping to. But if I slide it up all the way to the maximum value, you'll notice that the delay value drops to 50 and the light value reads as 974. And as I go between, look at the delay value starts to change, it starts to change, it starts to change, it starts to change, it keeps changing, boom. And I can slide it back and forth, slide it back and forth. And the map function, as you can see, is working properly. So now, all that's left to do, now that this is all working and we've used the serial monitor to help debug it, is we just need to add in the additional logic to turn on and off that onboard LED. Well, if you remember from lesson 1, we're going to do exactly the same thing. We're just going to change, instead of, 1,000, we're just going to input the value for delay value. And that's what we're going to do. So remember day 1? I'm going to actually just make that really easy for us here. Digital write, delay, digital write, delay. I'm going to just copy paste because that is a day 1 lesson. Digital write, LED built in, delay, digital write LED built in low, delay by delay value. Now, let's start the simulation for the final version of what should be for this project. Now, if I bring it to maximum value, you can see the delay on here. Actually, let's zoom in really close. It is apparently going so quick that you can't even see it. And if you delay it like this, it's obviously a little bit slower, 500, 500, 500. And then if I go quicker, it gets to the point where, honestly, you can't even really see it. So I'm actually going to change this instead to be so it's a little bit easier to see. And again, this is why we put it at the top. I'm going to say 200 maybe, and then I'm going to say this is going to be 1,000. Now let's restart that simulation. Let's set it up for this and that. And then here we go. Now it's blinking every second. Move it a little bit here. It's kind of like in between, going much faster. The light here, much, much faster. And then obviously here, it's blinking really, really fast. And we can actually see it this time. Because the simulator can't handle things that are lower than like 200. So with that, now we have the simulator for getting your battery up and working again. We got the charging systems, hopefully now all ready, wired up, simulated, and without further ado, I will see you guys tomorrow as we will continue the fixing of our solar array and battery to get you guys back home. Adios.